has gone dark.
Maddie, can you hear me?
Yes, I can.
Go for it. We're live.
Thank you, Bobby. This is Maddie. Cheers. Welcome to Radical Democracy. And I am here today with our very special guest, Dr. Alberto Conti, to talk science. We seem to live in a time when we expect our children to learn science. We expect everybody to learn science. And yet we seem to have a little disrespect for science right now. We have a lot of people in government and around in other areas of our lives that seem to question a lot of what scientists are telling us. And I'm not saying that because I don't think we should question. I think we should question everything. But I'm also very curious about why we seem to have this, not quite a disrespect, but almost a disinterest at times in science. So I asked Alberto if he could join us, and I'm going to start by asking him to tell us a little bit about why he became so interested in science. Thank you for being here.
Thank you, Maddie. It's a pleasure to be here. So as Maddie has said, my name is Alberto Conti. I'm an astrophysicist, and I became, let's say, obsessed, I think, with science and astronomy in general. I was given a telescope when I was 12. I was born in Italy, and I used to drag my father in very cold nights up there in the Alps to take a look at the stars. And so I think that from the beginning, so to speak, I started being a little obsessed about the why of things and the how of things, and I kept asking questions and questions and questions, and that led me to, sort of ultimately coming here, working for either industry or government in the United States to build a telescope to ask questions that I think are much bigger than myself, and questions that are very, very hard, and questions that have been sort of asked by perhaps mankind since the dawn of time, if you will. So it's and I became very interested in general with questions like where do we come from and where things come from? Are we alone in the universe? And so it's been an obsession for the last 50 years or so.
Oh, wonderful. So I want to ask you a question. So if you were going to talk to people about astrophysics or astronomy right now, what would you say are the most important, wonderful things we all need to know?
We all need to know. I don't know if you have enough time because it's a very large topic, because astrophysics and cosmology and the history and the study of astrophysics over the last, I would say, century has changed dramatically. So when you asked me, to join you, I jotted down a couple of things that I think are remarkable in a sense that represent the progress that humanity has made over the last, let's say, 100 years. And so perhaps not everybody knows, but we live in a conglomerate of stars that we call the Milky Way. There are about 200 billion stars in our Milky Way, and our Milky Way is one of billions of galaxies in the universe. And it might not become a surprise to you, but we did not know this until very recently. Just at the beginning of the last century, less than 100 years ago, we had no idea there were galaxies outside our own galaxy. So we didn't know that there were billions of other worlds outside our own, basically, that had the potential to perhaps generate planets like our planet. And so one of the things that was discovered in 1929 was that the fact that our own universe was filled with this. They were called nebulae at the time. They were called nebulosities, things that were not really resolved by telescope. We couldn't really see them, and folks did not know how far those were. Did not know if they were island universes, as they used to be called, like our own. And so, in 1929, Edwin Hubble, who became very famous because of the discovery of the expansion of the universe, realized that, oh, wait a second, there are other galaxies out there. And in one night, basically, in 1929, we discovered that our universe was, billions and billions of times larger than we ever thought it was, right? And so I don't know if this fact is known by people. In a sense, I don't know if people know that the universe is so large, right? The other thing that I thought was interesting is I don't know if people have realized that to this day we don't know that about 94% of the universe is unknown to us, right? We thought we knew what the universe was made of, right? And then until the 1930s, we discovered that there was a lot of stuff that we can't see, but we feel that its presence through gravity, so to speak, was there, and we didn't know that it was there, and that accounts for about a quarter of the universe. And then just in the last few decades, we realized that our universe is expanding at a much faster rate than it has been, and that is filled with this energy that we don't know. And here's a little trick for you, actually, to know when astronomers are BSing you or not. Astronomers, when they don't know something, they call something dark. So dark energy is this energy that fills the universe that we have no idea what it is, and that fills 75% of the universe. And dark matter, another dark, right, which is this matter that basically has about 25% of the universe, is also something we have no idea about. So we use these words that are dark to tell us about things that we don't know. So these are a couple of things. I mean, I can go on and on and on. Maybe the last thing I want to say, actually, there's one thing which is important, is that when I went to graduate school, 20 years ago or so, we knew about maybe 3 planets outside our solar system. We know we have 8 or 9 planets, depending on what you think about Pluto, whatever you want to put Pluto. But let's say we have 8 planets in our solar system, and we did not know until about 6 years ago that if there were planets outside our solar system. But what we also know now, thanks to a satellite called Kepler that was launched 7 years ago, that not only our solar system is pretty common. There's so many solar systems out there in our own galaxy, but also that there are planets around the stars, or like our own galaxy, like our own sun. And some of these planets might be habitable, might support life. And so this is revolutionary, because since just over the last decade, we have expanded our horizon yet again to understand that perhaps we're really not alone in the universe. So,
well, that's wonderful to know. And I also am curious about what it is that we call the scientific method. I mean, we seem to have a problem nowadays in some arenas with the facts. What are facts? So, and what are not facts? And I think perhaps people don't quite understand how scientists arrive at these things that we call facts. And, when science is made simple enough, in some of the articles I've read lately, especially on climate change and articles on the expansion of the universe, people can make it simple enough to understand. So, but the method itself of how people get there, like the use of charts, is wonderful. Of course, we're not. Oh, and let me say to my audience, I apologize. We are doing this remotely, so I cannot take call-ins, and I am seeming to have a little bit of trouble looking at comments. So I'm sorry if I'm not answering your comments directly, but we're going to go on with the show anyway. So that's my concern. My concern is that we do all this questioning of facts because maybe we don't understand how these facts became known to us to begin with.
Right. So I think there's a lot of questions in what you just asked me. So let me see if I can untangle a couple. No. I think it's very important, but I think it's one of the things that I always say is that part of the role of science, and what science to me is basically trying to figure out how nature works. What is the world telling us about how the sun shines, how the earth goes around the sun, how weather changes on the planet? And so I think it's almost like one of those Sherlock Holmes mysteries, right? We have clues, and we have to figure out who the culprit is, what is generating these changes, what is generating the climate, and what is generating the heat that we see on Earth, for example, right? And so, as I was telling you perhaps earlier, I do believe that science is like being in love almost, right? You have to, when you're in love, you want to tell everybody, and so you want to talk to everybody about how wonderful, all these clues that nature is giving you. And so, over the course of the last 2-3 millennia, humans have developed this method that we now call the scientific method. It was not called the scientific method. And by the way, I'm going to give an example maybe later. Everybody uses that in their daily life. They just don't call it that, right? But it's a way to basically arrive at a at a fact or to arrive at a conclusion that is based on some evidence that you gather, right? And so over the last, again, millennia, we developed this method, right? And this method is, I'm telling you right now, is not perfect because science is not perfect, but it's also a method that has built in almost a error correcting system, right? Mm-hmm. In a sense that it's a method that is freely available to anybody. Anybody can come to the same conclusion or different conclusion than you do based on similar facts. There's a discussion that takes place and stuff like that. And so the example that I usually give for to young kids when I talk to them about the scientific method is, let's assume that, Maddie, you have a toaster, right?
Right.
So you have a toaster in your kitchen, and you go and try to toast your bread in the morning, and the toaster doesn't work, right? So what do? You ask, you make an observation, which is my toaster does not toast the bread, right? So I, as an astrophysicist, might make an observation like there are the planets outside the solar system, for example, right? So the first thing you have to observe something, you have to look at nature, right? And so your toaster in this case is nature, right? It's a pretty bad example for nature, but it's nature, right? Okay, so the second thing is, so you ask yourself a question after you make an observation that your toaster is not working, and the question is, why doesn't my toaster working? Why doesn't it toast the bread that I have, in the toaster, right? And then you just you yourself ask yourself, okay, maybe the toaster is not toasting because it's broken or something, or maybe the outlet where the toaster is plugged in is broken. So let's assume that you think that the outlet is broken, right? Mm-hmm. And so you basically you have a working hypothesis, so to speak, right? Which is you basically decide that I'm going to test to see if indeed this outlet is broken, and so you make a prediction, so to speak, right? Which is that if you unplug the plug from one outlet and plug it to the other outlet, if the other outlet is not broken, then you will have your toast, right? So your prediction is if the other outlet is working, then my toast will work. And then you test your prediction, right? You make a prediction, you test it, right? And the testing is what? Well, you plug the thing in, and then you toast your bread. And if your bread gets toasted, then you say, fantastic, I've discovered that the outlet is broken, right?
Right.
And if it doesn't work, then you say, well, I have to go back to the drawing board because my initial hypothesis, which is that the outlet is broken, is not valid. So I have to go back and say, what else could it be? And oftentimes in humans, it happens that maybe the toaster wasn't plugged in or something. I don't know, right? To begin with. But
happens to me a lot.
So everybody in their daily life does this, right? And so this is a silly example, but one of the most incredible examples of this is when a fellow that many of you might have heard of, Albert Einstein, right? Mm-hmm. He was a clerk in a patent office, right, in Switzerland, and he decided that to look at some of the facts that were in front of him, in particular about gravity, talk about how things fall and what happens to things falling, and he decided that some of the facts that he saw, they really not fit a pattern. So he saw a broken toaster, basically, so to speak, right? And he decided why is the toast broken? And in order for him to develop his new theory of gravity, he had to throw away almost everything that had been done before by Newton and that has stood as law, if you will, the law of gravitation for the last 300 years, right? Mm-hmm. So I'm just telling you this because you can see that anyone that has an idea that is better than the idea before that in science can emerge as a champion for that, right? Right. And so he proposed this method. It was called crazy at the beginning. It was called things were crazy. But as we did with the toaster, where we made a prediction, what happens if I plug it in a different outlet? He made a prediction, and the prediction was that if the theory of gravity that I developed, that is an extension of what Newton did, is valid, then here's the prediction. The prediction was that if you look at stars near the sun, you will see them in a slightly different position because the gravity changes the position of stars with respect to what you see, right? And the prediction was proven true, which was an incredible feat of engineering, not of engineering, but of imagination, if you will, right? Yeah. And by the way, he did do this by just pen and paper, right? Mm. He just did pen and paper. He was a guy that was not at a famous university. He was a person. And so there's almost a democratizing, sort of aspect of science, which is anyone has an idea that is based on on observations about nature, observations about, climate in that case, right? In this case, can indeed bring forward the observation and just say, I have a better explanation, and this is why. And I quantify this explanation by telling you that this is a prediction that I make that is different than the prediction that previous theorists perhaps make, right? And that makes my theory stand apart, right? And if, by the way, if Einstein had made that prediction would have been wrong, then his entire cathedral of ideas would have been wrong, right?
Right.
So it's a pretty high bar to pass, but it's a bar that has been proven very, very successful over the past, hundreds of years, actually, right?
So we were talking earlier about how, and something you just mentioned before, about how science is like democracy and about how the principles of democracy and how that government is supposed to work, that style of government, and how that is part of what makes science so exciting.
Yeah, so that's the interesting thing. So when you asked me to come here, I was thinking about what is really science, right? How we define science. Forget about the method and how we go at it and find things, but what is really what does it really mean to do science? And I think science to me is a lot like democracy in a sense. It's a free exchange of ideas for the purpose of finding out, in the case of science, basic rules of nature, how nature works, right? Democracy is basically the free exchange of ideas to figure out how we can evolve, how we can how we can communicate and collaborate in society, right? So it's very similar in that, right?
Right.
Without the open communication, science doesn't work, right? So when I told you about the example of Einstein or anybody else, basically, when they put forward a new theory, the theory is tested, but the theory is also reviewed, if you will, by other experts in the field, right?
Right.
So, and that's very important because they can tell you, you got it right up to here, but then this portion is perhaps wrong, and this is why, and we think you're wrong. And so, science is very conducive to debates, to arguments, arguments where we talk about things, and democracy is like that. But at the same time, I mean, science is also pretty messy, right? Mm-hmm. The process of figuring out how nature works is pretty hard. We made a lot of mistakes. We are humans. We make mistakes. We have assumptions that we make because we see the world and how the world is. And here's an assumption that lots of people might have, which is wrong. We think that on Earth, and because of the law of gravity, things fall at the same rate. And so if you have something that is heavier than something else, so a ball, let's say a bowling ball and a piece of feather, you think they fall at different rates, so they hit the ground differently when you let them go. And the reason is because you observe that, right? But if you remove, like they've done many times, if you remove the air in the atmosphere, for example, they fall at the same rate, which is a prediction of gravity, for example, right? So this is to tell you that how perception of nature and your everyday life can be counterintuitive in determining the laws of nature, because there are other things at play, right?
Right.
And so the fact that anyone can come up with a good idea and be tested, the fact that these ideas are, we call it peer review, reviewed by your peers.
Right.
And your peers, I'm one of those peers. They can be pretty nasty because they basically, if I come to you and tell you, this theory that you just put up is wrong, and this is why, you're going to be pretty upset. So you're going to try to go back and forth, and we're humans, right? But the process is actually pretty solid and pretty established. And through error, through trial and error, things at the end, almost always, they bubble at the top. So things are well-established facts, like gravity, right? Like light, like the fact that the electromagnetic force where my computer is standing right now is what's keeping the table together, for example, right? So those are things that are established facts because there's an amount of evidence that is there's a large amount of evidence, right? And so science has to base itself on facts like these, on things like of things that can be let's say repeated with success, if you will, right? So I can drop a pen, I can drop a ball, I can drop anything, and gravity will always behave identically, right? And if it doesn't, maybe we learn something about gravity or something. So it's a system of ideas, if you will. It's a way of thinking, I would say, that is conducive to new ideas. There's no forbidden idea in science, right? You can ask any question, right? Any question you want, and you just have to be a little careful sometimes. I guess we mentioned this before. Like perhaps some politicians and folks in democracy come out as arrogant because they think they know the answer to things. Science can be arrogant, and sometimes it can be perceived as arrogant because we think we know answers to things. And in some instances we do, in some instances we don't. But the purpose of science is just basically to try to replace, your belief system with some hard evidence, with some facts, right?
Right.
I don't know if I'm answering your question, but
no, that's perfect, because I think when we observe what's going on in politics today, we don't have that. We are not debating ideas. We are not peer reviewing. We are not looking like. I believe, and I'm really not sure whether he's been misquoted, but the quote has been attributed to Einstein, that he was the one that said the definition of insanity is doing the same thing over and over again and expecting a different result.
Right.
And that seems to me what we're doing in government today. We need to be applying more of that scientific method, and we certainly need to be applying more of the democratic approach to how we are going to solve our problems. The beauty of science to me, and of course, having been raised by a scientist, but I was raised by a scientist and an artist, the beauty of science to me is that it looks for solutions. So when I started this program, when I went on this journey of campaigning, the whole idea behind it is to look at solutions, and that's not what we're doing right now. I actually think we could apply the scientific method to government, and we'd all be in better shape.
Maybe. So I think the difference that I see is that I'm not sure there are laws of government, right?
Mm-hmm.
There are laws of science, meaning, and by laws I mean, laws are not things like they're not set in stone. They're just observations about nature, like gravity or like light, for example, things like that, right?
Right.
Or like that the water boils at 100 degrees Celsius or whatever, 212 Fahrenheit, right? Those are facts that are well established, right? Those are laws of nature when things change, right? I'm not sure you can make an analogy with the laws of democracy, right? Because people can choose not to respect each other, for example.
Right.
People choose not to listen to each other. And so there's a breakdown. So I don't know, there are social laws, social behaviors, right?
Right.
And I think we're demonstrating right now that those behaviors are pretty bad.
Yes.
But I think, so that's the difference. So I'm not an expert in sociology or human behavior, but I think people have been trying for a long time, probably, to devise some laws that apply to people, right?
Yeah.
And I can think of some laws that do apply to people, which is that there's a law in physics in general. It's the law of large numbers. So when I bet I can predict pretty accurately, I should say, the behavior of large crowds, for example.
Right.
Right? Because they act almost like I don't want to say an organism, but they act like as a large collection of people that all go and do similar things, right? So predict the behavior of a single person that can change, like they do in politics and in democracy, the course of history. I think that's very hard, and so that's why I became a scientist and not a politician. I want to stay out of things that are not that don't have any evidence-based. But I don't know. Maybe I'm wrong, right? Maybe I'm wrong. Maybe there's some laws, right?
Well, I do sometimes think it goes back to something you said earlier, where we might have to evolve to the point where science is about looking at nature, and science is, to me, also about improving the human condition. There's that element of science. It's not just the curiosity, but it's also, I think, about making life on Earth better for everybody. Right. So I think that's one of the more admirable things about science and scientists, at least the ones that I know. So the other thing is, I wanted to bring up something I brought up in the past on the show, which is both Jack Ma and Bill Gates have said things like we have to change the way we are educating our children, that we are that we're going to live in a world in 30 years where almost everything that it can physically be done by a computer or a robot will be done by them and be done better and faster and more efficiently than a human can do it. So we need to educate our children to be the creators, to have values, to understand how teamwork develops ideas, to be able to think outside the box, to be critical thinkers, to be able to peer review, things of that nature, that education needs to change in that direction. So what would you have to say to all of that?
Oh, there you go, on the spot. So I think, so I have a couple of things. So I think one thing is that we have to recognize that as we have evolved through time as a species, right? The way we have learned has changed because the tools that we have at our disposal are different, right?
Right.
So I didn't grow up with the beginning. I didn't grow up with Google, right?
Right.
Neither do you,
No.
right? So I didn't grow up with having in my fingerprints every single information I can possibly have, right?
Right.
And that, to some extent, that's a big positive in a sense that we have democratized information, if you will, across the globe. But at the same time, without a scientific method or some metric, if you will, to assess accuracy of the facts of the things we presented online, right? It's pretty hard to judge if my opinion is different than your opinion, and why my opinion is based on fact and yours is not, for example, right?
Right.
That is very hard to do, right? And so I think what we need to do is realize that the repetitive, I think, portion of the work that we're going to do, the manufacturing jobs and the things, you're right, they're probably going to be done by robots, right?
Mm-hmm.
But those are not the most creative portions of what humanity does, I think,
Right.
in my opinion, right? The more creative things is people, inventing new tools to make our life better. People figuring out how to make us live longer because with some tools, or people trying to figure out how to preserve our planet so billions more of us can live on this planet, happily without destroying the planet itself, right?
Right.
So I think what we need to change is, in my opinion, is two things, right? So one is the way we teach has to be somehow try to evolve with the time we're in, right?
Right.
So when you as a teacher, I don't know, you do this for a living, so I'm telling you something you probably know already, but when you have to fight with 10-second or 20-second span of attention,
Right.
To get your point across, because you're going to be otherwise, sort of trumped by a video on YouTube or by some text message that comes in or something like that. That is really hard to do, right?
Right.
And the second thing is, and so I don't have the answer to the first one, right? I don't know how we regain some sort of control of those eyeballs that are our children's eyeballs when it comes to learning, right?
Right.
They seem that they want to learn things fast, and sometimes the process of science is neither nice nor fast nor clean, or sometimes it takes time to investigate. Things are sometimes complex, right? So I don't know how we restructure our education system so that we do give a little more thought to some things. And one thing we definitely need to teach, by the way, is a way for us to figure out how to judge headlines in newspapers or headlines and things to figure out if is there something that is true of it, behind that or not, right?
Right.
So that's part of the issue. The second thing is, I think we also have to realize that, and I think we know it, but I don't know if you realize this, that we are much more connected than we have ever been in our species, right?
Right.
I mean, not just because we take planes everywhere that can go across the ocean, but because of communications and because of the result of globalization of communications, also the flattening of cultures, right? Their cultural identities are being kind of flattened because we all going to kind of, approach the same level. We're going to learn all the kind of the same things. And so I think one of the things that we have to pay more attention to is how, as we grow as a species, as we grow with our differences, can we preserve some of our identities while at the same time, trying to preserve our ability to live together, to share the resources of the planet, to share the the things that planet has had to offer. And I think right now we're still acting. I say this to many of my friends. We're still acting like animals, right? We're still pretty primitive in the way we interact with each other, right?
Yep.
Despite all this abundance of information and facts. And so you have to ask, where is this all going? If I can access all the information and I have access to all the things, how come? When I talk to someone about evolution, which is a pretty well-known and established theory, right? About how we all came together. Why is it that I have to debate folks that are that they basically say they don't believe, they don't accept this as science, or when we tell them that there's that we have a measure to establish how old the universe is, right? And this is why we do it. How come some people don't believe that, right? And then fundamentally, I want to end this, but fundamentally, one of the things I want to say is that there's no reason to believe. Science doesn't believe anything, right? There's nothing to believe in, right?
Right.
You just experience the universe, nature. You gather some of the laws that are embedded in nature, and you ask questions and say, "Can I?" Here's my little symbols that I write on a piece of paper. They're mathematic symbols that can approximate the behavior of nature, right? I can adjust, and so I don't have to believe. I don't have to believe in gravity, right?
Right.
There's nothing I have to believe in the sense that gravity is just a way that nature works, right? And so I don't know how we do and take this, the scientific method and put it into the hands of kids. One thing that I know that we should definitely do, and you probably know so much more about this than I do, but we need to, I think we need to reestablish some sort of a goal not a goal, but we need to some sort of a way to engage the new generation to be curious as I was when I was a kid, for example, right?
Right.
Because right now, it seems like after 10 seconds, they read the headline, they move away, for example, right? So I don't know how to engage those eyeballs. And you probably have experience. You have experience with very young generations, right?
Yes.
And you see that firsthand, I assume, right?
Yep.
So I don't know what the answer is to that, right?
Well, I think actually there are some answers in the science of psychology and human development.
Yeah.
Certainly in terms of human development and brain development, we do know what we should be teaching and how we should be teaching it at a certain age. What's so frustrating for me and so many teachers and so many people involved in education is we are not listening to the science. We are not looking at what the science says. We are not. I think that's why you had people like Jack Ma and Bill Gates and Harari coming out and saying, guys, it's like they want to shake us. I feel that way. That greed, that's really what is happening is greed is, in my opinion, forcing us to function on a much lower level than what we have evolved to be as human beings. That everything is about money. Everything is about what the price tag is, so that you end up with this very distorted view of what anything can be, even if it's been scientifically proven. So we've said to people, here's how human beings develop. Here's how the brain develops. Here's what you should be doing at those times. Oh, but if I can make money doing some standardized testing, which we know does absolutely zero, all of the scientific evidence tells us absolutely zero to educate a child or improve education in any way. But there's money to be made there, so we're going to keep that in. So, yeah, you're right. It is an uphill battle to deal with children, to get children, to keep them, not get them to, because we start out curious. We start out wanting to look at all these things. It's keeping them curious that is the problem. And that goes back to another famous Einstein quote about something like, it's amazing to me that curiosity survives public education at all. And when did he say that? It's got to be back in the 40s, right? So,
Yeah, it's like every generation has their grumpy person that says, my generation was better. So I don't want to be that grumpy person, right?
Right.
But I do want to figure out how, and maybe, I don't know. I mean, I deal less with young kids than you do by far. But I don't know what the level of curiosity is. I'm just afraid that when you have when you have access to any information you want, and you're presented with information that is somehow selected because you only see the information from your friends, right? Or your information from sources you trusted that never question your beliefs. Well, that is a problem, right?
Yes.
You need to question why you're seeing this. You know, is it to ask why, right? And you have to ask how things work. Why am I seeing what am I seeing, right? And so to me, that is the beauty of science. But I don't know how you work with kids to make them see that it's beautiful. I mean, to me, when I grew up, the curiosity came from the fact that I wanted to know, right? So how would I do now if I were a kid right now, growing up, where all I can do is to do my homework? I can just Google it. Right. How would I was reading an article the other day where there are kids that are using Alexa to ask solution for problems, right? So to do algebra, to do things like that. And so what I'm afraid is sometimes you have to be a little careful, right? There's a lot of creativity, but if the creativity comes at the cost of a overall dumbing, we're going to dumb ourselves because we're going to offset our answers and our intellectual ability to some machine or something without questioning the results of the machine. And by the way, the machine is probably right 95% of the time.
Right.
But that doesn't matter, right? You need to be able to question that, right? So
yeah.
So I don't know how you do that. So I think science and scientific method are a way to approach that. I think the scientific method and the way we approach, a little example about the toaster there, shows that there's a way that you implicitly do this every day, right? When things don't work, when your printer doesn't work, why do they write, is it plugged in?
Right.
That's part of the scientific method, right? Well, observations, printer's not working. Well, first, the second thing, is it not working because it's not plugged in? Okay, so those are the things that are simple, that are, that we can put forward, and where the scientific method might help, right? The issue is that I think to some, science might seem kind of tedious. Might seem kind of a little boring. Might seem kind of not as exciting as it is, right? And so I don't know how you probably know how to make it exciting, I guess, and for the next generations. But I think part of the issue is that I think we need to acknowledge that there's an issue with the way we teach, right?
Yeah. Well, we need to acknowledge that there are issues with many different things that are going on in the world right now, and one of the things that we need to acknowledge the most is something you said earlier. How are we going to solve the problem of let's say of the world at large facing climate change? That is a very big issue. That is an issue that just came up again. And something you said earlier when we were talking was very impressive in terms of you as a scientist, when you said that when you look at the statistics, 97% of scientists agree that the world, the heating up of the world, the global warming, the climate change has a basis in what human beings are doing, in human behavior on many different levels. It's not just one thing. It's many different things. And yes, the 3% that disagree could be right, like you had said. They could be right. There's the whole majority of one thing. There's that sometimes one voice is the right voice.
Absolutely.
And sometimes 50,000 people can do a foolish thing and it's still a foolish thing. And the one person can do the right thing and it's still the right thing. But I think when we're dealing with something as threatening as climate change could be, don't you think we should be erring on the side of caution here? Even if the 3% are right, it's still going on, right?
I totally agree. And so I think the way I think about that is, again, in sort of probabilistic terms. So let's say, I don't do this, but lots of people buy lottery tickets, right?
Right.
Okay. So the probability that you win a lottery ticket is 1 in a billion or something, right?
Right.
But you still think you might have a chance. You feel okay. So what if when you look at climate change, the probability that the large majority of the scientists, because I look at the data, are going the right direction, is more like 97%. It's a large number, right? So as I told you before, maybe those 3% are right, okay? And so science is a way to actually assess if they're right or not, right? We all look at this with the same data. By the way, there's no censorship. The data is available. It's available online. It's available from NASA. It's available from sources that are across the planet, not just the United States, for example.
Right.
Satellites that have been in orbit for decades, core samples taken in Antarctica, and measurements of pollution from satellites that have been in orbit for decades, buoys that measure temperatures, ocean temperatures, the concentration of, I'm just naming things right off the top of my head, concentration of carbon dioxide, for example, in the sea level. So let's say that these 3% folks are right. They still have to explain to us what is causing what we think is this increase in temperature, why is the sea becoming, I was just watching a documentary last night, why is the sea getting hotter, the ocean's getting hotter and all the corals are getting bleached,
Right.
Why is that happening, right? Well, we know why the corals get bleached. They get bleached because the temperature of the ocean increases by a few degrees, right? So why does it increase by a few degrees, okay? So you can say, maybe it's an anomaly, maybe it's the sun. So we go and look at the sun and we look at the data of the sun and the variations of the sun against the variations of the planet, and we see that the correlation is not there. There's no correlation between what really the sun is doing, because the sun is not changing that drastically to call for this, right? Plus, the sun has been doing this for a while, okay? For like 4.5 billion years now, right? And we have a record that goes back to, millions of years actually. And the sun was actually doing this for a while, getting a little hotter, getting a little colder, but we don't see the same trend, right? We don't see a trend in temperatures, right, for example. And so you have to question, there's nothing wrong in claiming that that there's a different source of the heating of the planet or something, but we have to show what the source is, right?
Right.
And so I think those 3% perhaps are arguing something different, but the overwhelming majority is basically arguing that what is causing this increase in temperature and the change and the climate change so drastically is that we're injecting a lot of carbon dioxide in the atmosphere, right? And so one of the statistics I can give you is that over the last decade, we have injected more carbon dioxide in the atmosphere than we had for the past 300 years or so, right? And so, and the amount of carbon dioxide we inject in the atmosphere is a significant percentage, 10%, 15% of the entire atmosphere, right?
Right.
So when you change a system by injecting, new things into the system, like like the Earth system, if you will, when you add this much carbon dioxide, something might happen. I'm not an expert in this, so I don't want to claim that the direct result is that the Earth is getting warmer, but something happens, right?
Right.
And most of the folks think that, and they have the 97% folks have a lot of science behind them to show them why carbon dioxide is a gas trapping, why, you would know this. People that have their gardens, that have their greenhouses know that a greenhouse, is warmer than the outside. That's why it's a greenhouse, right?
Right.
And the reason is that you trapped a lot of the gases inside, and these gases they trap the sunlight. They're transparent. Your greenhouses are transparent to the sunlight, but then a lot of the heat stays in, right? And with carbon dioxide, is no different. So that heat has to go somewhere, and it goes into the atmosphere a little bit, not too much, but it goes in the water, for example. And so there are going to be changes. And so I think this is established. I think what is clear is that there are forces, if you will, folks that in the name of
greed.
I don't know if it's greed, but maybe it's in the name of established industrial practices, I say, or other things, might argue that that this effect is not as large. Might argue that this effect is not as important. Might argue that this effect is not caused by humans, for example, right? And so I have no problem with that. But the argument has to be on scientific ground. The argument has to be following the scientific method, again, to show me, here's your evidence, here's why we think that, that our explanation works. Because if the explanation doesn't work, we have to go back to the drawing board and figure out what works, right?
Right.
And so I think that's why I think I'm a little depressed sometimes at how we easily dismiss climate change or some very hard facts about science just because we feel that cannot happen. Like an argument I hear all the time, which is frankly pretty silly, about climate change is that, it's very cold this winter, therefore therefore there's no climate change, right?
Right.
And people fail to understand that this is the overall temperature across the entire planet. So while it could be the coldest winter in the United States, let's say last year, for example, it's probably one of the warmest times in, I don't know, in South Africa or in Australia, right? And so you have to average it out. And we humans are not very good at taking things that we know as in our everyday experience and trying to extrapolate them to things that we have a hard time understanding. Like the Earth is a very complicated system, right?
Right.
But at the same time, we have to follow the trail, the crumbs where they lead, right? And so where we wanted to go is to try to understand why changes are happening to the planet, right?
Yes.
And so, and by the way, we have examples. I can tell you this as a statement with high reliability. I don't want to call it fact, but there are other examples of carbon dioxide causing exactly the same runaway effect on other bodies in the solar system, namely in Venus. So Venus is a planet that is a little smaller than Earth. It's closer to the sun. It gets a little more energy from the sun, but its atmosphere is mostly carbon dioxide. And so what happens is that since carbon dioxide traps heat, the surface of Venus, even though it doesn't receive that much more energy compared to us on Earth, the surface of the planet is about 600 degrees Fahrenheit, right? So it's pretty hot. Okay, and only because the atmosphere is really thick and the heat can't get out. So we have an example that is sort of gas is trapped in the atmosphere act like this. We have example in the laboratory. When you go in the lab, you can analyze this. And there's a lot of, I can go into detail, but there's a lot of issue of clear science that shows you why carbon dioxide is particularly, and methane and things like that are particularly dangerous for trapping heat, because during the day, let's say, let me give you a quick example. So during the day, the Earth heats up when the side of the Earth is close to the sun heats up. So there's a lot of heat that shines through the atmosphere. It's the Earth. It bounces off the Earth and it goes to the clouds, but it also bounces in the atmosphere and it excites. Basically, some of the energy from the sun goes into molecules of carbon dioxide, and these molecules start vibrating. They absorb this heat, right? At night, this vibration turns out to, at night when the sun is on the opposite side, this vibration is this heat that they collect during the day is released in the form of light, but this light is actually called infrared, which is heat, what you and I call heat, right? So the heat from the sun is absorbed during the day and released during the night. As overall, if the more carbon dioxide you have in the atmosphere, the more trapping abilities you have, and the more you increase the temperature, like happened on Venus. So I think that's a pretty well-known fact. So if you want to dispute these facts, you have to have, as Carl Sagan used to say, if you want to, claims are extraordinary claims really require extraordinary evidence. So you have to show me what is the evidence that supports that, right? And I think that's part of the problem right now. We take everything we see at face value without looking a little behind the curtain a little bit. It doesn't take too much. You actually Google something and look at this, right?
So, I'm sorry, we had a brief interruption there. I apologize for that, that brief interruption. Technical difficulties, not being a computer scientist at all, me. So yes, this is exactly it. This is exactly what you're saying is exactly the problem we face. And I feel like what has happened in politics is that everything is being used for politics. Everything is being used to advance people who want to stay in power, as opposed to advancing actual knowledge and actual solutions. So, like, where carbon sequestering might sound really good on paper, is it really getting rid of the carbon in the atmosphere? If you're trading, we're just paying this country to use their carbon, their allotment of carbon. So then it becomes about money again. And this is a very frustrating cycle for us human beings here that would like to have a planet for our children to live on for the next 7 generations. So before we run out of time, and we're about to, I just wanted to ask you a little bit about your work on the Hubble and the James Webb, and the importance of governments funding science, of private people funding these great explorations, because again, we are back to, well, we have to save the people on Earth first, and then we can spend money on that. But I think you're arguing apples and oranges, in my opinion. I think we have to do both at the same time. So I just want to.
So I'm biased in this, obviously.
Yeah, please be.
Because I used to work for NASA for a while, and then I worked for industry as well. But I think it's, so I think when you think about telescopes like the Hubble Space Telescope, folks, I've known about Hubble. Probably, some of your listeners have learned about Hubble and they heard about Hubble. So this is a telescope that's been in orbit for 28 years. The orbit's about 500 kilometers, 360 miles above your head. Basically, it's been doing this for 28 years, and it has really changed the way we look at the universe, right? So Hubble, for example, told us the age of the universe. He told us there are other planets other than our own solar system planets. He told us that, as I was mentioning to you at the beginning, that, that 94% of the universe, we had no freaking clue what it is, right? So he told us that, right? And this is a tiny little instrument that it was built by ingenuity by humans, but with the key support of a very, key support of NASA, which is a very forward-thinking agency that thought that sure we are taking care of our own here on Earth, but we also are explorers. We always been explorers, right? We need to explore the unknown. We need to be curious, And I think, in my opinion, if you think about what NASA does, right? NASA is sort of the curiosity of in this case, or the American people, but it's our curiosity because it shows us things that we even didn't know that were possible, right? So as I told you, NASA launched a little tiny telescope that was aimed at looking at other planets to figure out if they were habitable. And instead of finding a few, we find a ton of them, right? And again, I didn't know about this 10 years ago. You didn't know. So we didn't know our place in the universe until 100 years ago. We didn't know there were more planets out there. And so what NASA does, I think, with Hubble in particular, what it's done is really changed. It almost like I will almost call it another revolution. There was the Galilean revolution, which is that we are not at the center of the solar system. I'm sorry, the Earth is not. The Earth is just one of the planets. And then the Copernican revolution, which also said, after we've seen all these planets going around, we're just one of them, for example, right? But the other thing is also the next revolution is at some point we're going to figure out that we are just part of a larger collection of planets that might have life, for example. And so NASA actually, since it's pretty forward-looking, they are looking for to build telescopes. And so the successor to the Hubble, the scientific successor to the Hubble, will be the James Webb Space Telescope. And this telescope is it's going to be roughly 100 times more powerful than Hubble Space Telescope. So it's going to be launched in 2021. And the telescope is like a marvel of engineering because it was built to answer really four questions. I'll give you two of them, which are pretty striking. One is when did the first stars ever form in the universe? And so ever means we're going to look at 13.6 billion years into the past and look at the life from the first stars ever, right? And that's mind-boggling to me that I can even ask that question, right? That's mind-boggling, right? That we know the age of the universe, that we know when stars. And then closer to us, for the first time in our history, we are at a place, again in history, because of our ingenuity, where we're going to be able to ask the question, are we alone in the universe, right? So we're going to look at other planets around other stars and ask, can they support life? Can we see maybe signs of life? And so Webb is built to do in the solar neighborhood nearby exactly that. Which, if you think about it, that's a question that humans have been asking forever, right? And now we are part of the generation that can actually say we can start building the instruments that can start really answering the question. And no other generation has done that before, right? If that doesn't inspire you, I don't know what.
I'm with you. I'm with you 100%. And I also think that it's important to look at the best and the brightest. We can't be so egalitarian that there's a tendency to say, oh, well, I can't talk about how smart he is because she's going to feel bad because she's not that smart. But it all goes back, again, here we are with Einstein, which is, we make people feel stupid. If we don't say that you're as smart at creating art, or you're as smart at creating music as Alberto is at creating telescopes, and we put everything on that equal basis, all of our creation, all of our creativity is helping each other, is raising up all of us. So if we look at everything on that level, it's going to be creative thinking that raises up the children in poverty, that makes us, that it's creative thinking, in my opinion, to break down the walls of education, which are basing how we fund education in this country on property taxes. Of course, education is going to be unequal. I don't care if you're teaching exactly the same thing; it will be forever unequal. So we have to break down things that we have believed in always, which is not to say we won't find that they're true ultimately, but it's to say that the beauty of being human is to question, to explore, to connect, to rediscover, and to work as a team.
I agree. I was actually going to say, I'm going to give you homework.
Oh,
that's on something else, which is great. So maybe one of the things that we could do for the next generation is give them a sense of purpose, in a sense to try to push us forward as a species, right? Where are we going as a species? I mean, I don't think we're going to go anywhere. We're going to keep fighting each other on ridiculous issues, right? But we might go somewhere else if you're starting getting curious about how to fix the problems that we have here, about how we can explore for the future, right? And that's the curiosity that we should all have, I think, right? I am biased, and I'm very lucky to be able to ask and try to get answers to the questions I have. But part of what we could do, and I don't know how you do it, but you should do it, is try to excite these young generations to see that there is kind of beauty in discovering things that have never been discovered, beauty in improving the life of your fellow human just by a little bit, right?
Well, and I don't think it's that difficult to excite.
Yeah,
I mean, children are naturally curious, and they are naturally kind. They are naturally, we as human beings, maybe we should just start calling them little human beings. Maybe one of the problems I think people have in dealing with children is we don't look at them as young, small versions of ourselves. We look at them as a separate species. And
they are sometimes.
And they are sometimes, yes. There are moments where you definitely think they're a separate species, but they're not. So we have to understand that if we are born with all this curiosity, if we are born with all this kindness and connection for each other, there's obviously a reason for that, whether you believe it's some spiritual reason or you just believe that it's a reason, it's there to help us survive. If you just look at it simply, strictly as a survival mechanism,
I agree with you.
We are better.
Yeah. So I don't know the answer if we're born or not with that, but it's irrelevant to some extent, right?
Right.
In the sense that I think I have not seen a human being that is not curious.
Yep.
And so we need to capture that somehow and try to figure out how to bottle that up. But that's your job.
And I accept. So on that note, I would just like to thank you so much for being on, and maybe at some point even come back and talk a little bit more about the James Webb and what's going on with astrophysics and all of that wonderful, amazing stuff. And I would just like to also say that next week, again, will not be a call-in because Kay Olin, Mohawk Wolf Clan, will be calling in to discuss their democracy, which we discuss very often, to discuss the great law of peace and other aspects of that. Again, she will be calling in. And I also want to, again, thank Bobby Lucera. Thank you so much for arranging this so that we could all be here tonight. I want to apologize for anybody who was posting comments as they were listening because somehow I just couldn't pull it up here. So I do apologize if I didn't get to you. Hopefully next week when I'm back in the studio, everything will be fine. Thank you all for listening. Bye-bye.